So in this video we're going to go through just some introductory stuff about physics as a science, and as well as scientific notation and significant figures and calculating numbers with significant figures. So first, just an outline. So with the course motivation, we're talking about applications and the fact that it's a science, and we'll get into the typical discussion of theory, hypothesis, fact, stuff like that, as well as the math that you're going to need in this class. Then we'll talk about significant figures, and then scientific notation. And discussion of significant figures, strangely enough, will give us a motivation for the use of scientific notation, which is a little bit different from the typical motivation that's often discussed with this topic. So, something that many of you may know is that physics is considered one of the pure sciences, along with biology and chemistry, but you would really consider this one to be the purest one because physics is the one that's most like math. In other words, like on the one hand you have biology, which is mostly conceptual, memorization, and that type of thing. And on the other hand you have physics, which is nearly all math. And in the middle you have chemistry, which is somewhat of a mixture of both. But really any field that requires the use of mathematics and logic from fundamental principles must often turn to physics. And this is the subject that used to be called natural philosophy a number of centuries ago, before it really grew into what we now call physics. And theoretically, none of you actually need this class, because since it's just natural philosophy, then you should be able to use your incredibly brilliant mathematical and logical skills to derive everything that you're going to learn in class. But in practice, unless your name is one of these really, really famous people among a handful of others, then you're really going to need to experience a lot of these topics first before you'll be able to come to an understanding of how and why you apply certain logic and math in a correct way in order to solve problems and come to necessary conclusions. So, in a quick summary, physics is the study of the universe as a whole, but it's also the study of all of the parts that make it up, and including a lot of the applications that we have in the world around us of various devices and everything that you use. Physics is really important for understanding how these work and in being able to build them. And it also has a lot of applications to other fields like chemistry and biology, because chemistry at its fundamental level is based upon quantum mechanics, thermodynamics, and statistical mechanics, and these are all subfields of physics which will be covered throughout AP Physics 1 and AP Physics 2, mainly AP Physics 2 with those. In biology, of course, it's based upon chemistry, and that gives you the link to physics there. And also, a lot of the same logic that's used in understanding of evolution by natural selection is the same logic that's used in order to understand how to do physics. In fact, in the past, there have been a number of really good evolutionary biologists who got their start in physics because the same type of logical principles apply in understanding both of those. And since I have an astronomy background, I will often stress the applications to astronomy, because astronomy is the biggest laboratory for physics in which to test physics. It's really physics on the grandest possible scale. And the direct application of physical principles into astronomy is often called astrophysics, but the degree to which we'll apply those in this class is not really what you would typically call astrophysics. It's more going to be of a more fundamental, or I guess an easier nature. It's not going to get into the really nasty math of astrophysics. It's really just going to be at the level of algebra 1, algebra 2, geometry, and trigonometry, so which is stuff that you're supposed to be quite familiar with in this class anyway. But astronomy is a really interesting subject in its own right, and it has a lot of very awesome applications of physics in it, so we'll discuss those when we have the chance. Now, of course, there are a lot of everyday applications of physics. For example, maglev trains operate by superconductivity, microprocessors. In fact, for that matter, any electronic device that you're going to come across has a lot of physics applications in it. Cars and any engineering field is very deeply rooted in physics. And there are a lot of course, well-known areas. Obviously, rockets and spacecraft have very strong physics applications, as well as nuclear warfare, electron microscopes, MRI machines, and nanotechnology, which is one of the big fields that's still developing. In fact, it's believed that in the next decade or so, there are going to be a lot more jobs in fields like nanotechnology and similar types of fields. In fact, the vast majority of the jobs out there in a decade or so will be in technical fields. So that's one of the other motivations to learn physics in general. You need it for your future job. And of course, these are just a few of the applications. If you take the time to think about it, though, you'll find that physics is present everywhere. Now, physics is, of course, a science. Science is built upon laws, facts, theories, and hypotheses, and as such, physics is a science. So, laws are generalizations about things that tend to be true. You often think of it as like, oh, it's a law, it's really, really important. Some laws are important, some of them aren't so important. And we'll see what actually is so important very soon. Now, facts are just that. They're true statements about some well-defined notion. So here is an example of a fact. The physical characteristics of populations of animals tend to change when you look at different ages in the fossil record. That's the process of evolution. That doesn't necessarily by itself imply that one group of animals evolved from another group of animals, but it is a fact stating that different groups of animals lived on this planet at different time periods. And an example of a law would be that massive objects attract each other through a universal force, which we call gravity, and it's the same force that causes objects to fall on Earth. It's a nice generalization, and by itself it's definitely true, but without equations attached to it and without other items coming from it, it might not necessarily be all that useful. But theories are items that actually take into account facts, laws, logic, mathematics, and a lot of other things at times to create a general statement not only about how a physical process behaves, but also about why the process works. And that's what makes theories the grandest things that you can come across in science, because they can be used to make future predictions. They are extremely useful. So, in accordance with the fact that we stated just a little while ago, an example of a theory would be that the observed evolution of animals in fossil records due to the process of natural selection, where there's a source of variation, and animals with variations that allow them to better adapt to their environment are favored versus those who don't have these favorable variations, and those who don't have these variations tend to be selected against. In other words, they are less likely to pass on their genetically favorable variations to the next generation. So this is the theory of evolution by natural selection. It's not the only theory of evolution out there. When you hear people say, oh, evolution is just a theory, it's like, no, evolution is a fact. There are theories of evolution, and biologists sometimes heavily debate with each other about which theory of evolution is better than some other theory of evolution. It doesn't always occur by natural selection. Nonetheless, evolution by natural selection is a very useful theory for describing the vast majority of the broad instances of evolution in biology. A nice possible counterexample to theory of evolution by natural selection would be the Cambrian explosion 500 million years ago. And it was a period of rapid evolution, definitely evolution there, but it's looked at now, it might not have all occurred by natural selection. There might have been some other means. In fact, the laws of physics seem to be very nicely built into how the evolution occurred at that time, but that's getting a little sidetracked now. But, as I said before, physics is a science. And recall, in science, the really great achievements are theories. And these are, in fact, laws and facts often derive from theories, because the theories are able to be used to produce laws and allow us to verify and discover new facts. Now, again, sometimes the word theory is misused in popular parlance. For example, people say, oh, it's just a theory. In fact, that's something you'll sometimes hear applied to biological evolution, as if being, quote, just a theory is a bad thing in science. But no. The problem is that in popular language, the word theory is more similar to what we in science would call a hypothesis, whereas in science, a theory is what we really work for. It's the grand explanation for why all of the facts and laws are the way they are. And typically a good theory has been tested very, very well over and over again, and it's been improved and modified so that what we have now in our theory is a really good, grand understanding about why things are the way they are. And biological evolution by natural selection is an example of such. It's a great explanation of how evolution has occurred throughout time and how we have obtained the current variation of species that exists on this planet. And it's been tested by a lot of different mechanisms. So, for example, as I mentioned before, biological evolution is a fact. It's been proven not only by observed changes in the fossil record, which by itself wouldn't necessarily imply that one species derived from another, but simply suggests it, but now we have a process called mitochondrial DNA sequencing, which actually does verify that one species evolved from another, which may or may not be extinct. Generally, the original species is extinct, but not always. And what this process of mitochondrial DNA sequencing has been used to successfully derive lineages of many animals, sometimes even with some surprising results. For example, now we know that storks are not so much related to herons and egrets and that group of birds, but they're actually pretty closely related to condors and vultures, which is kind of neat. But anyway, so Charles Darwin's idea of evolution by natural selection is an example of a theory because it tells us how and why the observed evolution in the fossil record actually took place. Now, in physics, we have similar types of situations. For example, there is a fact that the orbits of planets, which are ellipses orbiting around our sun, the orientation of these orbits actually shifts very slightly from year to year. And this was very puzzling for people. It was a violation of Newton's law of universal gravitation. Notice the law was wrong. But general relativity, which we consider a theory, a very good theory, actually successfully explained why this precession occurs, and it was able to make a direct prediction of exactly how much precession we should expect. And that prediction has been confirmed not only with the case in which it was originally found and motivated, but also in a wide variety of new cases as well. For example, elliptical orbits with neutron stars and stuff like that. A lot of it goes back to gravitational radiation. Now, good theories are what we really work for, and a good theory is something that is able to explain a whole lot of stuff that's within that theory's framework. In other words, if that theory makes a definite prediction of something that you realize, yeah, that's something that theory really should be able to discuss, then it would be surprising if that prediction turned out to be wrong. You would either question the testing mechanism or the experimental setup, and if all of those ended up checking out and you kept reperforming that experiment, and you still ended up getting a different result, you would realize that theory is probably not very good. It needs to be either modified, or if that's not enough, maybe even abandoned for a different theory. Now, the amount of math in physics depends greatly on the level in which you're studying. In the highest levels, a lot of times math fields are developed specifically to satisfy theories that are developed in physics. And one of the earliest examples of this was Isaac Newton inventing the field that we now call calculus, so that he would be able to explain the orbits of planets and the paths of projectiles and similar types of phenomena. Now, the amount of math that you're going to need to be able to do in AP Physics 1, well, you need to have a very good understanding of Algebra 1, Geometry, and Algebra 2. Like, you really need to know these fields really well and remember just about everything that you've learned in them. And you should also be relatively comfortable with sines, cosines, and tangents from elementary trigonometry, which hopefully you were already exposed to in either geometry or some class before that. And it's important to note that this class is very math heavy. You'll do every bit as much math in this class as you will in your math class, most likely. And that might be an exaggeration compared with the calculus classes, but for most of the math classes, yeah, this is a class that it's essentially a math class. It's an applied math class. So you should be fairly strong in math. Otherwise, it's going to be more difficult for you in this class because we're going to be going through the math relatively quickly because it's assumed that you already know that, so that we can concentrate more on the physics, which is what you're here to actually learn. And if you're not very comfortable with the math, then you might, if it's real bad, you might want to consider dropping down a level. If otherwise, you might want to just check out an Algebra 2 book or an elementary trig book from the library and study the necessary concepts from that. So now it's on to the main event, what we're actually doing in this class. So one of the first important aspects of any quantitative science is an understanding of how good your measurements are. And a lot of this goes into what we call significant figures. And what we mean by that is how precisely can you confidently state that physical quantity was measured. For example, if you just write something as 5 inches, that's a lot less precise than saying that it's 5.0000 inches. The first one has one significant figure, the 5, whereas the next one has 5 significant figures, the 5, and then that 0, that 0, that 0, and don't forget, that 0. So this states that the idea here is that it's like, okay, the 5 is, somebody rounded it from somewhere between 4.5 and 5.5, and the 5.0000 was rounded from somewhere between 4.99995 and 5.00005. So the rules for counting significant figures are that zeros that are in between the first and last non-zero digits, these are counted. So it's like you just count the numbers there, and zeros between first and last non-zero digits, those are counted. But you don't count zeros to the left of a first non-zero number and a decimal number. For example, if I said 0.0035, you would not count those first zeros. You start counting at the 35. And once we start talking about scientific notation, that might make even more sense. But you do count zeros to the right of the last non-zero number in any decimal number. For example, that 5.0000. We count those because the idea is like, okay, what could this have been rounded from? Those extra zeros give us more information about that. So the number 50 has one significant figure, with the idea being that it was rounded from somewhere between 45 and 55. But if I wanted to denote that the actual physical measurement was probably between 49.5 and 50.5, I would write 50 dot. And some people write a line over the 0 or under the 0 to denote that that 0 is indeed significant. So to say that, yeah, this actually has two significant figures. 50.0 has three significant figures, but 0.005 only has one. Again, we ignore these leading zeros, but you can make this have three sig figs by adding two more zeros here, because these actually say, hey, we actually know this number real well, at least reasonably well, to the 100,000th place, as opposed to simply the thousandth place. And 5.005 actually does have four significant figures, because the idea is like, okay, this is a number that we have counted 5 whole numbers here, and we've been able to measure it to the nearest thousandth. So that's four significant figures. Now, when you're multiplying or dividing a bunch of physical measurements that have varying levels of significant figures, then your answer is only as good as the number that had the least number of significant figures. So for example, in this problem right here, the 4.1 is the number that has the least number of significant figures. It only has 2, with the idea being it's like, okay, this was rounded from somewhere between 4.05 and 4.15, which means that this whole number is potentially off by a certain percentage, which means this whole answer is going to be off by a certain percentage, which, using our rules of significant figures, means that this answer is only good to 2 significant figures. Now, the real way of saying how good this 15.08 is, it's a little bit more complicated than that, having to do with relative error, and the rules for that are derived using calculus, so we're not actually going to worry about that. You can actually do it without calculus. It's actually something very similar to the Pythagorean theorem, but we don't do that at the AP level. That's something that's sometimes done in college. In fact, it's often done in college, but it's not part of the AP curriculum. So we're just going to worry about significant figures and say, hey, this is a product of a number with 3 sig figs times 4 sig figs over 4 sig figs and 4 sig figs. So the number with 2 sig figs limits our estimation of this result. In other words, it's not really 15.08, it's 15.08 plus or minus the amount by which this could have varied due to the 4.1. So we say 2 sig figs, it's 15. Something else to notice, we didn't round until the very end, because if we had rounded each one and said, oh, this is only good to 2 sig figs, no, that would be introducing an additional error, which we don't want to do. Introducing additional errors in the middle of a calculation is bad. We don't like to do that. So we don't round anything until the very end. That's something that's very important to remember when we get into calculations with what I like to call hybrid problems. In other words, a mixture of multiplication division with addition subtraction. And we'll get to that sometime. Now, when you're adding and subtracting different physical quantities, what's important is not the number of significant figures. It's the number of decimal places. In other words, what we call the level of precision. So here's an example. Let's say you have 35.2 plus 2.46 plus 0.001. Well, the 35.2 is known to the nearest tenths place. This is known to the nearest hundredths place, and this is known to the nearest thousandths place. Again, consider what would have been involved in a real physical measurement that was rounded to these. In other words, for example, this was really somewhere between 2.455 and 2.465. And you can come up with similar statements for the other two numbers. So it's because of these potential rounding results that give us our rule here, that when you add and subtract numbers with different levels of precision, it's the least precise number, in other words, the decimal place or the placeholder, that influences this. In other words, since this was rounded to the nearest tenth, and these others were rounded to levels more precise than that, when you add and subtract these types of numbers, the result is only going to be good to the nearest tenth, because these other two numbers, yeah, they came from other numbers that went into the calculation, but this rounding right here to the nearest tenth means that a nearest tenth error was introduced, which means this is only good to the nearest tenth. So this needs to be rounded to 37.7. Now notice, yeah, it has 3 significant figures, which was the same number of significant figures that had. That's a coincidence, because look at this. This only has 1 significant figure right here. So we didn't count significant figures at all in this calculation. All we cared about was the decimal place, the fact that this is only good to the nearest tenth. And again, don't round until the very end, otherwise you'll be introducing additional errors. In fact, the rule that I like to state is, when you're considering rounding, ask yourself this question: am I about to put a box around this number denoting that it's my final answer? If the answer is no, then you don't round yet. If the answer is yes, then yeah, you should round to either the correct number of significant figures or the correct level of precision. And again, this came out due to the fact that this was the least precise number in this calculation. So some more examples. Let's say you have this number, 7600 plus 4 plus 46.7. So 7600 is the least precise, so we need to round our answer to the nearest hundred, because this is only good to the hundreds place. So 7700. Whereas meanwhile, in this next example, the 2.02 was the least precise number. Well, let's see. That's good to the hundredths place, whereas this one's good to the 100,000ths place, and this one's good to the millionths place. Well, hundredths place sounds less precise than those others, so the answer here needs to be rounded to the hundredths place. So 1.98. And finally, in our last example, 180,000 minus 24,420 minus 31,086. Well, the answer is going to be 120,000, rounded to the nearest 10,000ths place, because that's what we got here. And these other two numbers are more precise than that. So the fact that this number right here could be off by as much as 5,000 due to rounding means that this could have been off by as much as 5,000 due to rounding. Now, before we go on, I should mention something concerning math class. You might say, well, my math teacher would disagree with this. I don't think so, because your math teacher is dealing with numbers that are by definition infinitely precise, whereas these numbers are not infinitely precise. We're saying that these come from physical measurements. We've made that claim. Now, I could say that this 4 right here was part of an equation, And if this 4 was part of an equation, then we would say that the 4 was infinitely precise. In other words, if it's not a physical quantity but simply a constant in an equation, then we pretend that it's 4.0000000, etc., and deal with the numbers that actually are physical quantities. So just wanted to clear that up before any confusion arises because of that. Something else to mention is the fact that if you had been bad and said, oh, I want to round everything to the nearest 10,000 ahead of time, then this would be 180,000 minus 20,000 minus 30,000, and that would turn out to be 130,000, which is not what we got. We would have rounded too early. Bad, bad, bad. Don't round too early. Now, here's another example with addition and subtraction. So let's say you want to add these three numbers together. Well, when you do that, you realize, okay, it's only going to be good to the tens place because of this 320. So I want to denote my answer is going to be good to the tens place. So when I round that, I get 5,300, which might at first seem good. But then you think, well, wait a second, 5,300 is good to the hundreds place. But I want to denote that it's good to the tens place. Well, you could put a bar above it, which I don't like because it might denote that it's like, oh, it's that continuing. So one way around this is to use scientific notation and write it as 5.30 times 10 to the third, because 5,300, so it's 1,000, so 10 to the third. But the 5.30 actually denotes, hey, that 0 here is significant. It's a real digit. We want it. So that's one possible motivation for scientific notation. So just a review of scientific notation in case you need it. So here we're talking about some number with possibly a decimal rate times 10 to some power. For example, we would write 632.7 as 6.327 times 10 to the second. And that would also denote that it has 4 sig figs in it. And 4.26 would be written as 4.26 times 10, or sorry, 0.000426 would be written as 4.26 times 10 to the minus 4, also denoting that it has 3 sig figs. So when you write numbers using scientific notation, the coefficient, in other words, what's multiplying the 10 to the exponent, always has a very straightforward number of significant figures. It's whatever's listed, however many digits you say. Now, it doesn't necessarily tell you anything about precision. To get precision, you would have to write it back in standard form, like how these numbers are written. So, for example, Earth's distance from the Sun, 93 million miles. You would write that as 9.300000 times 10 to the 7th. And notice how we got there. We say, okay, it's really 93 million dot, and let's just assume that these zeros are not significant, so just call it 9.3 times 10 to the 7, but this is 93 million dot, or 9,300,000 times 10, move it over 1, or 930,000 times 100, or 93,000 times 1,000, which is 10 to the third, or 9,300 times 10 to the 4, or 930 times 10 to the 5th, or 93 times 10 to the 6th, or, there we go, 9.3 times 10 to the 7. So there is another explanation of how scientific notation works. So just thinking now, it's like, okay, what exponent should be here? Well, to get this, we must have moved this decimal over 1, 2, 3, 4, 5, 6, 7 places. So we get an exponent of 7. And how about over here? 3, 6, 9, 10 places, so an exponent of 10. How about here? 3, 6, 7, 8, so an exponent of 8. And over here, 3, 6, so an exponent of 6. Now, you can also just practice with, like, okay, what should be the number here? Well, if it's times 10 to the 8, this would be 7.34. And if this is times 10 to the 11, it would be 8.7, assuming 2 sig figs. And if this is 90 billion, so we would move it all the way over to here to get that 10, and it would just be 9 with 1 significant figure. And here are some more examples with that process as well. Now, let's say you have a number that's less than 1. For example, like how would you write the mass of an E. coli bacterium? So if it's 0.000000000000665 kilograms. Well, here's the other big motivation for scientific notation. It allows you to write numbers like this in a nice, tidy, compact form. But the idea is that, okay, if I was to magically move the decimal place over by 1, I would have to multiply by 1/10 in order to get the same number again. So in other words, if I magically moved the decimal place over, you think, okay, that's the same thing as the decimal place being over here divided by 10. Or if I moved it over twice, that's the same thing as the decimal place being over here divided by 100. Or 3 times over 10 to the third, 4 times over 10 to the fourth, 5 times over 10 to the fifth, here over 10 to the sixth, here over 10 to the 7th, here over 10 to the 8th, here over 10 to the 9th, here over 10 to the 10th, here over 10 to the 11th, here over 10 to the 12th, or if you move the decimal place over to here, it's the same thing as this number would be the same thing as the decimal place over here divided by 10 to the 13th, or times 10 to the minus 13th. So if you move the decimal place over to the right, your exponent's going to be negative. In other words, negative exponents are numbers less than 1. Positive exponents are numbers greater than 1. So a number of different ways of remembering this. So 3.4 times 10 to the fifth in scientific notation, if you wanted to convert it back, then you would just move the decimal place back, and there it is in standard form. So try these. Just think to yourself to make sure that these are correct. And again, there are a number of different reasons to use scientific notation. It's a way of allowing correct use of significant figures if it's not very convenient to do so, and it gives you a very tractable way to write really big or really small numbers in relatively compact form. Now, it also gives you a way of dealing with numbers that don't have any significant figures at all, also known as numbers that are only known to within an order of magnitude. For example, to within an order of magnitude, the number of stars in the visible universe is 10 to the 22nd. Gosh, that's enormous. It's like 10 billion trillion. It's an incredible number of stars, but nonetheless, we don't know the exact number, but we're fairly sure that it's probably somewhere between 10 to the 21 and 10 to the 23rd, and 10 to the 22 seems like is a pretty good estimate for that. Now, if I was to tell you, oh, it's 3.2 times 10 to the 22, no, that's foolish. We don't know that to that level of precision, but 10 to the 22 is a pretty good estimate. So how about a calculation with scientific notation? Well, here's that old example before where we got 5,300. Well, if we put it in scientific notation, that denotes that this 0 right here actually is important due to the fact, hey, this calculation is good to the nearest 10, and that would be where this 0 flies. Now, here's another calculation. Let's say I want to multiply this physical quantity, that's actually the mass of a proton, times this one, which is the speed of light. So in other words, we're getting the rest energy of a proton here. Remember the most famous equation in science, E equals mc squared. So if I recognize that, hey, these are good to what you have here, well, I say, okay, this is good to 9 significant figures times this being good to 5 significant figures. Well, my answer is good to 5 significant figures. So when I write it out, I should have 5 significant figures here multiplying the 10 to the minus 10. And again, with scientific notation, significant figures is very straightforward. So there's my final answer. I should actually mention real quick though, even though it doesn't look like it, this number is actually exact. The speed of light is given as a definition. It's exactly this number of meters per second. So this actually has an infinite number of significant figures. But we don't care here because this only has 5 anyway. So 5 is less than 9, so it's definitely less than infinity. Now, a lot of people sometimes wonder, how do you enter stuff into your calculator with scientific notation? So what you do is if I wanted to enter 1.29 times 10 to the 6th, instead of literally typing 1.29 star 10 caret 6, I would write 1.29 and then I'd press the special EE key. The location of this key is different depending on your calculator, and then I would just write 6. And that would literally be 1.29 times 10 to the 6th. The screen would say it would display it like this, 1.29 little capital E, 6, and that would tell you that it's 1.29 times 10 to the 6th. Now, if you want a number with a negative exponent, well, you just enter it like that after the EE. So the mass of this proton in kilograms would be 1.6726 times 10 to the minus 27, or 1.6726, and you type E, you press the EE key. Just press it once, don't press it twice, because the key is EE, and then negative 27, and then press enter, and that it would display on the screen, kind of like that. Now, people often ask, well, since my calculator spits out numbers in scientific notation like that, can I write my answers like that? And the answer is no! Because if you write it like that, we would consider it wrong. In fact, what would be even worse would be using a lowercase e, which is the base of the natural logarithm, and that's clearly wrong. So the only acceptable way of writing these numbers is not using computer notation, but simply, if it spat out this number, then you would need to write it as 1.5033 times 10 to the minus 10. That's how you need to write the number. So if you write it incorrectly using this type of calculator computer notation, I would mark it wrong. I wouldn't take off all the credit, but I would take off some points. Now, here's another example using something. Let's say I wanted to calculate this. Well, my answer, it turns out, is good to 4 significant figures, because the numbers 4 and pi are actually exact. In other words, you might even recognize this. This is the formula for the surface area of a sphere with a radius given by this number, which is actually the radius of Earth in meters. So the 4 and the pi are going to be exact because they are part of the formula. So the answer is good to 4 sig figs, so 5.112 times 10 to the 14. And if this is meters, then this answer would be meters squared for the units. Now, this answer is important because if you don't apply the rules of significant figures and precision, your answers will literally be wrong. So let's say you decided to find the volume of a sphere that has a radius measured to be 0.14 meters. Well, that's only 2 significant figures. But what would happen if you assumed that it was infinitely precise? Well, you know that the true value is somewhere between 0.135 and 0.145 meters. In other words, the true value was somewhere between here, and it was rounded to 0.14 meters. So the answers that you would get from your calculator if you plugged in 0.135 meters, 0.14 meters, and 0.145 meters are given by this. In other words, the true volume of the sphere is somewhere between this number and this number. So stating that it's the middle one, which you got by the 0.14, saying, oh, it's exactly 0.011494040321935 meters cubed, that would be wrong, because the probability that it is that is incredibly small. It's actually somewhere between here and here. Now, in truth, yeah, it's more likely that it's closer to this than it is to either of these, but nonetheless, you don't know exactly what it is. The best you can say is that it's 0.011 meters, because your given was only 2 significant figures. That was the only given. It's a multiplication problem, so you would say that it's 0.011 meters cubed. So stating either of these other numbers would be quite wrong. Now you might wonder, it's like, well, how can I say that how can I even say 0.011 if it could be 0.010 and 0.013? In other words, it seems maybe our significant figures rule failed for this. And the answer is, it actually kind of did fail. It's a little bit different when you have exponents and stuff like that. The true rule is a little bit more complicated. Again, it's the one that I mentioned before that we're not going to get into concerning relative error, but we'll, for the purposes of AP Physics 1 and AP Physics 2, for that matter, we pretend that it does work like that. And you're never going to be off by more than about 1 or 2 in the last number anyway. So we'll call it 0.011 meters cubed and be happy. So just a summary of what we've talked about in this lecture so far, in this presentation. The truth of a physical answer should not depend on how many decimal places your calculator can spit out. In other words, it should only be based upon how well you actually know the answer, or at least believe its value to be, based on the measurements that went into the calculation. And notice that if the rules of significant figures had been applied correctly in the last problem, we would have had 0.011 cubic meters, and it actually is reasonably close to the extreme values and the discrepancies are due to the fact that these errors increase when you're dealing with exponents, and we're not dealing with the actual true correct rule. The true correct rule, though, is very close to the much simpler rule that we're using here. So with multiplication, you're dealing with multiplication and division, you're dealing with significant figures. With addition and subtraction, you're dealing with level of precision. Now, what we'll get to next time is what happens when you are dealing with a combination of these. For example, we have a lot of physics formulas that are combinations of multiplication, division, and addition, subtraction. In fact, some of the most basic formulas that you'll have to know are exactly like that. So the question is, how do we deal with it in those situations? That's what we'll talk about next time. But in the meantime, I'd like to focus your attention on the following. Consider, and we'll discuss this in class as well, how many significant figures would be implied by stating a time, a time of 4 hours and 6 minutes. How about 4 hours and 12 minutes? Would they be different in any way? So that's something to think about, and then you'll discuss that with each other next time. Thank you.